So we are very happy to have Nava uh, talking about black hole Eikonal and information paradox. He has been working with Gerhard Tuft on this for some time, and now he has his own program on this, I guess. So he will be talking about his recent results. So Nava, over to you.
Yes, thank you very much, Ayan. I'm very happy to be giving this talk. It's not often that I interact with Indian string theory these days, so it's very nice. It's also an honor to be speaking. Thank you. So indeed, I will talk about what I will define as the black hole Eikonal. I've highlighted in red because it's something that I will hopefully explain in detail, and I will talk about how this is an interesting phase of quantum gravity, and how this is related to and in my view resolves a version of the information paradox. So hopefully I will explain all of these things in this talk today. So this talk is based on these three papers largely. Uh, these these are works that have been done over the last 2 years, but were put out in the archive towards the end of last year. The first and the second one were with a student. He was a master student who will now begin a PhD with us, Nico Groenenboom and Gerard het Hoofd. And the last paper that you see is with a couple of collaborators of mine, Panos Betsios and Olga Papadoulaki. Panos he's in Crete and Paris now. He will move to Canada. And Olga is in ICTP Trieste, and she will move to Perimeter this fall. I will make some references to some older work of ours, but predominantly the talk will be about the first two papers that you see here, and possibly a little bit about the third. So here's a rough overview of my talk. What I will discuss is, firstly, as something that I hope most of you are familiar with, I will discuss how an information paradox in the way Hawking envisioned it, how that arises because of considering free field theory with no gravitational interactions in curved space-time. I will review that in the beginning, and then I will move on to discuss how gravitational interactions can be introduced. And I will take a very well-known old example of the flat space Eikonal phase of quantum gravity. I will discuss that in detail. I will tell you how this can be modified, this can be adapted to realize a new Eikonal phase near the black hole horizon, and how including interactions in that region resolves an information paradox. And I will finish with some conclusions and an outlook. So let's begin with free field theory in curved space. Please feel free to stop me at any point, complain, raise questions. As interactive, the more interactive, the better. I don't really have to get to the end of my talk. If I'm delayed by a lot, I will somehow find a way to reach some conclusions. But I hope that wherever I stop, most of you will be on board by then. So here's a free field theory that Hawking considered, which is Einstein-Hilbert term with a minimally coupled scalar field. And for most of this talk, I will focus on the vacuum solution, also often called the Schwarzschild solution. Unfortunately, Johannes Droster's name is missing out in most of the references. He wrote a paper shortly, a couple of months after Schwarzschild, and his paper is probably most resembling of the modern day solution that we use. So here's the solution. It's a spherically symmetric solution. It's static, time independent. And here's a Penrose diagram that possibly most of you have seen. I've included an extra year at the top to suggest that this black hole could potentially evaporate. And one may also ask how such a black hole forms. And here's another very naive picture where here I'm considering infalling null matter. So there's some matter that you send in between V equals V naught and V equals V1. It falls in, collapses into a black hole, some horizon forms, and at late times, this looks essentially like the Schwarzschild horizon. However, it's interesting or important to note that the event horizon is not exactly the horizon always. As the matter collapses, when you're closer to V equals V0, you see that as you go towards R equals 0, a very small apparent horizon forms, and that apparent horizon grows as more and more matter falls in. And by the end of it, the apparent horizon agrees with the event horizon, or they look very similar. And the solution gains some sort of an approximate time independence in this sense. Typically, this collapse, the time scale of this collapse is much shorter than, say, how long it takes for the black hole to evaporate. So at late times, Hawking considers that this is a good enough approximation to study fields for the Schwarzschild solution, even though this black hole might have dynamically formed during collapse and evaporates later. So here's another Penrose diagram that Hawking considered in his paper. This is in different coordinates. Here time runs bottom to top, so upwards. And here the collapse is modeled by curved lines, so this is not really null matter. But you see the event horizon is marked in bold black lines, probably not as visible as I'd have liked. And there's a singularity, which is a wiggly line at the center. So with these, I will keep using these pictures to illustrate various points throughout the talk. So what Hawking tried to do was to look at this vacuum solution, perturb around the solution. So here he considers G mu nu to be Schwarzschild solution, and look at metric perturbations and a vacuum. So it's a vacuum solution. So you have a vanishing background for the scalar field. So for the matter part of the action, you have the familiar Klein-Gordon matter action for the scalar field on this background. In principle, you also have free gravitons. These come from the metric fluctuations. But as long as we stick to quadratic order, these free gravitons essentially don't interact with the matter fields. So we sort of ignore them. So what we're going to do, I'm essentially reviewing what Hawking did, is consider the Klein-Gordon equation on this spacetime. So we're looking at the quadratic action for the matter field. And to solve this thing, or to understand properties of this field, we're going to use symmetries that are available. So we use the spherical symmetry. So I expand the field in spherical harmonics, YLMs, and I also expand it in plane waves. It's a time-independent solution. So essentially, the equation reduces to a one-dimensional equation in terms of some radial coordinate. Sometimes it's more convenient to use this coordinate r star instead of r, which is defined as you see to the bottom right of the screen. And some equations are easier to see or write down, simpler to write down in R, and some others in R star. So I'll just use them interchangeably to illustrate various points. So for example, R equals 2gm is the horizon, and that implies that R star is negative infinity. And spatial asymptotic infinity is when R star is also positive infinity. You can have the same coordinates inside the horizon, and R star is negative infinity as you approach the horizon from the interior. And as you go to the singularity, it's plus infinity again. So as you see in this equation, there's a coordinate r star that I've redefined, but there's also this potential V for every spherical harmonic. And this potential is called the Regge-Wheeler potential. It's an effective classical potential that matter experiences because of the curvature of the space-time. Interestingly, this potential has a maximum at roughly around 3 GM. So it's of the order of the Schwarzschild radius outside of the black hole horizon. So it's a little further away. And that allows us to study physics in different regimes. So this allows for a separation of scales. So let me just plot this Regge-Wheeler potential. So I've plotted it for two angular momentum variables, so L equals 1 and L equals 10. And you see that this potential has a maximum, and then it goes, as you go to the singularity, it blows up. So and as you see, the barrier is greater and greater for larger and larger L's. So what this means is that if you have so just studying this potential more carefully, you will see that if you're far away to the right of this diagram, this is essentially as if there was no gravitational field because the potential sort of drops to zero. So this is asymptotic physics near infinity. So I'm looking at distances from the Schwarzschild horizon, which I write as R minus RS, which is much greater than 3 GM. So it's much greater than the maximum of the potential. So it's essentially like considering fields propagating in flat space. Then there's the opposite extreme, where you're arbitrarily close to the horizon. So where I think of R minus RS is roughly of the order of the Planck length. And that's what I try to draw is a pink shaded region near the event horizon, where you're so close that essentially physics is dominated by Planckian effects, and we don't really understand this very well. But thinking about this has been very fruitful. Many people have written many papers. I've missed out a lot of references, of course. Just as a highlight, maybe one of the things a couple of words that might ring a bell is the brick wall model of 't Hooft or the stretched horizon and so on. So thinking about this regime, even though we don't really know how to describe it and we don't know the microscopic degrees of freedom, has given us some insights that are useful. But there's an intermediate regime, which I've tried to do, where I hope you can see this in this sketch a little more clearly, all three regimes. So if you're far to the right in R, you're at the asymptotic flat space. If you're very close to the Schwarzschild horizon, then you're in this Planckian regime. But in between the potential barrier and the Schwarzschild horizon, which is where distances from the horizon are much greater than Planck length, but are much smaller than 3 GM. This is where you have some notion of an effective field theory in curved space, which describes the near horizon physics. Unfortunately, the Klein-Gordon equation is very difficult to solve, and there's no known closed form solutions on this background. So the potential is way too complicated to solve even the one-dimensional problem. However, you can think of a mode expansion for the scalar fields. And here I've schematically written them as expansions in terms of operators A and B, and expanded in terms of bases of solutions. The bases of solutions near the horizon have a very simple oscillatory behavior. A similar expansion can also be done in the interior as long as you're far away from the singularity. One thing that's interesting to note and is very important is that one of the solutions is purely ingoing, and this is valid when there are no gravitational interactions. And we'll see how to move away from this free field theory. So what Hawking did was he looked at fields that you see at Scri plus, so at future infinity. And he observed that as you trace all these modes back, all of them pile up near the horizon. So no matter how far separated they are at Scri plus, all of them appear to emanate from the region, the small diamond that you see near the horizon. And near the horizon, because they all pile up, you're allowed to look very locally on the horizon instead of covering the entire patch. So that means that locally near the horizon, you're allowed to focus on Rindler space. And there we know that there are modes there that can be expanded and can be observed to be thermal, they're thermally populated. And there's a relation and you trace them further back, and you can go all the way back to Scri minus, provided there are no interactions. And this allowed Hawking to write down the modes received at Scri plus, so outgoing modes, in terms of ingoing modes on Scri minus.
Sorry, can I interrupt?
Yes, please.
So this is not really an assumption, right? Thermal population comes out. I mean, so as far as when you convert this ingoing to outgoing modes, there is this this factor, which eventually becomes thermal once you trace out.
Correct. So this is not an assumption, but the assumption is that you're allowed to do this when there are no gravitational interactions as you trace them back to Scri minus, because you're considering free field theory. It's not obvious that the same carries through if you allow for interactions near the horizon.
So you're saying that the geometry, so this is purely comes from this geometric optics, right? This.
Yes, exactly. I'm saying that this geometric optics is valid in free field theory. And I will show you why there are corrections and how one should think about these corrections as we go on.
Okay, thanks.
Are there any other questions? Okay, so as Oyan just said, this is not an assumption that the outgoing modes are related to the ingoing modes via these coefficients. These are valid in the approximation that we worked in. It's called the geometric optics approximation. And working out a number operator, for example, using these Bogoliubov coefficients. I'm not going through the calculation, but this allows you to write down the number operator, and you see that it has some thermal population. So it looks like particles are created. And by psi here, I just refer to the fact that we're considering the scalar field not in flat space, but in some semi-classical black hole background. And this operator, as you see, has no cross correlations between omega and omega prime. And there's a thermal factor beta, which is related to the mass of the black hole or the temperature of the black hole. What I want to argue in this talk is that this ray tracing, and in particular, the free field theory that you use is not enough to capture all the dynamics. And what I want to argue is that there are gravitational interactions that are very important near the horizon, which if you just consider free fields, you don't really see. And that's where I want to head towards the end.
Just a naive question to begin with. you can always consider a very big black hole.
Yes.
Where even if you go very near the horizon, even that the curvatures will be small, right? And you could.
Yes.
So
indeed. So the curvatures will be small. What I will show is that even though curvatures are small, precisely because there's an emergent scale of the size of the horizon, the curvatures will still be small, but there is still a notion of gravitational interactions that are weak in some sense, but that become important if you consider all of the interactions in some controlled approximation. So if you can hold your thought as we go, I will describe exactly what they are, but please feel free to raise the same question as we go.
Okay.
But as you see, before I go to gravitational interactions near the horizon, I first want to describe how one should think about these gravitational interactions in flat space. That's what I will go to next. So are there any other questions? Let me pause for a few seconds to see if there's some other thoughts.
Hi, can I ask a question? Hello?
Yes. Yes,
hello?
Please.
Yeah, I mean, just picking up on Ayan's question. So do you mean some kind of post-Newtonian interaction? Is this what you mean when you said there's some gravitational interaction at the horizon or close to the horizon?
I have this on the next slide.
Okay.
So here's a putative path integral that you can think of. You're quicker than me. So I'm going to do exactly the same as before. So we have this perturbation around some vacuum solution. Of course, as I said here, I've written down what the operator is for the free graviton in terms of the background. So you have the box operator and all the covariant derivatives in terms of the background that you've chosen. But what do I mean by interactions? How do you introduce them? It's just considering higher order terms in this perturbation theory. So by interactions, I mean the first one that you can think of is the metric perturbation coupling to the stress tensor. And then, of course, you will have higher order terms, which are quartic couplings and then cubic graviton self interactions and so on. In principle, this is a never ending series. We all know that this theory is non-renormalizable. So there are lots of problems with this. But by interactions, I mean exactly these. And I want to argue that there's a controlled approximation where, there's a controlled phase in the theory where these can be incorporated without running into issues of non-renormalizability. And that's what I will describe in the rest of this talk. Does that answer your question, Shubho? Okay, so if something is not clear, please hit me back again. But by gravitational interactions, this is what I mean. I mean something that's that you're all familiar with. So what people have done in the past is to consider only this 3-point vertex. So you see that H mu nu couples to T mu nu, and T mu nu is quadratic in the field, in the matter field. So this is a 3-point vertex, and they've ignored the higher order terms. Whether you're allowed to do that, we will get back to it at the end. But in flat space, people have done this, and they try to consider all the Feynman diagrams that you can generate out of this sort of a consideration, this sort of an approximation. So of course, when you perturb in the background field method, not all metric perturbations are physical. So you need to gauge fix. You add some gauge fixing term. This is a covariant gauge that that possibly all of you are familiar with. And once you do this, you can write down the Feynman rules for the theory. So the scalar propagator is something that you're also familiar with. You have a graviton propagator. Because we're working around flat space, it's easy to write down. And then there's the interaction vertex that I just said. Now comes the important part of this story, which is that you focus on a specific regime, which nobody told you to, but it's something that you can choose. So you define Mandelstam variables, S and T, as you're familiar with from quantum field theory, and you focus on diagrams that are leading in S much greater than T, and then such that center of mass energies of the collisions are greater than the Planck energy. And that's highly energetic collisions. However, why are you allowed to do this? Naively, you would think that if you have head-on collisions that are highly energetic, you would produce some Planckian-sized black holes and so on. So this looks like it's a very out-of-control approximation to go to. However, there's an interesting phase where you make one additional assumption, which is that first, you assume that momentum transfer is negligible. And I will show you a picture on what that means. But the most important thing here is that you take the impact parameter to be larger than all other scales in the problem. So what that means is that you have particles that are colliding at extremely large energies, but they're very well separated in the transverse space. So they're not very close to each other. They're close to each other if you project them on a plane on the light cone, but in the transverse space, they're very far away. They're bigger than any other scale that you can think of. So essentially, you would think that if they're slowly moving particles that are very light, that are far away, they will essentially not gravitationally interact. But the statement here is that these interactions start to matter if particles are still very far away, but their collision energies are extremely large. And this is a phase in which this is a phase that's called the flat space Eikonal regime. And in this regime, it turns out that the diagrams that are leading look like this. These are the only dominant contributions in this phase. And so here you see that every diagram is just made out of the 3-point interaction that we started with and just additions thereof. So the first diagram to the far left is the tree level diagram. And then you have more and more graviton exchanges. So you have graviton propagators that run in these loops. So the second diagram is the second and third diagram are one loop diagrams. However, the third diagram, I've ignored graviton self-interaction, so it's just an interchanging of the legs. And then the one after that is a 2-loop diagram and so on. There are 6 such 2-loop diagrams with all possible exchanges of the legs, and you can go on. So how do you think of these collisions? Here's a naive picture again on the Penrose diagram. So think of a highly energetic particle, so drawn in red, excuse me. So it's a very light particle. So mass is much less than Planck mass. So I approximately think of this as a massless particle. And now think of a test field or a test particle drawn in green that is traveling towards this. What you expect to happen is that the red particle sort of kicks it further away along the direction of the momentum of the red particle. On the Penrose diagram, they look like they collide head on, but you should think of the green particle as being very well separated from the red particle in the transverse plane, so perpendicular to your screens. And even though they are very well separated, the energies of the collisions can be very large. You can approximately write down the order of the magnitude of energy as 1 over g Newton times the test mass of the particle. So there's large transverse separation. Impact parameters are very large. A center of mass energies can still be very high. And it's in this regime that you cannot ignore gravitational back reaction. What I want to say with that is just a statement that graviton exchanges do matter. They play a role. Good. There's a very interesting story that's related to this that unfortunately I won't be able to talk about. And that story is that, as you can see from this picture, you can ask whether there exists a classical solution, a nonlinear classical solution to Einstein's equations that satisfies some discontinuity of this kind. And that can be written down. And that was done by Penrose, Eichelberg, Sexer. And it was further improved upon by various other people later on. And it's a very well-studied effect. And more recently, since a very interesting and very important paper by Thibaut Damour in 2016, people have also started thinking about how classical observables can be manifest as on-shell quantum amplitudes. And those amplitudes arise via Feynman diagrams like the ones that I just showed you. So, but I won't have much time to discuss the details of that, but I just wanted to mention that because it's very important and there's a lot of activity going on. And it's something that one of you mentioned. This also is studied in the post-Newtonian approximation and so on. There's a lot of relevance to these and gravity waves and so on. So back to our Feynman diagrams, it turns out that you can resum all of these diagrams, provided you make the approximation that I made. And as I call that a flat space Eikonal approximation. And all of these can be resummed into writing down an amplitude. I haven't shown you the calculation, but one place to look for it is in the paper of 1992 by Kabat and Ortiz. It's a very nicely written paper. Was there a question?
Yeah, I wanted to ask a question on your previous slide.
Yes.
So these kind of things have been recently also considered in the context of chaos.
Correct.
Right. I mean, and such solutions has been constructed. And I think there was this, in the context of black holes, Hawking radiation, this was originally mentioned first by Verlinde, these kind of effects. And
the first paper that mentioned this effect was this paper in 1985 by Teddy Drey and Thoft.
Yeah. But I think in the context of, so I think what Verlinde pointed out is that once this red line goes in, the horizon is going to expand, right? And then there is a sensitivity. So you could either end up inside the other green line across the shock could either end up inside the black hole, or it can actually go out. And it's a very sensitive to this particular thing. So that's the origin of this chaos essentially. But for that, you have to put this red line sufficiently early in the past, sufficiently early in the past.
Correct. So there's something that's slightly confusing about this picture, and I don't have settled thoughts on it. This is indeed true that Verlinder's claimed this and they pointed this out. It may very well be right, but there's something that I don't understand about the story, and it's the following. If you look at the actual calculation of the nonlinear solution, because of these shifts, the mass of the black hole, the location of the horizon are all kept fixed. So you're in a quasi-adiabatic approximation where the red particle does not increase the mass in the actual technical calculation. Whether this can be interpreted as something that increases the mass and how that comes about is unclear to me.
Well, it's I think they considered it as a small perturbation on this background. So it's like probably a very small epsilon. Yeah, but I think what they were aware of this sensitivity, and they actually also redid the Hawking radiation, recomputed the Hawking radiation with such effects. They redid the Hawking's calculation with such effects put in.
Not on a black hole background. They did that in flat space, and that's true. And they argued that this is true. I will actually mention something about the Verlinders and the papers that you're talking about very soon.
Oh, okay.
But before I go to black holes, what I wanted to point out was that as in the Eikonal phase in flat space, you can resum all these amplitudes. Remember that there are no black holes here. I'm just perturbing around flat space. And you can write the amplitude as you see at the bottom of your screen in green. So all the other variables I've defined, G Newton and S is just the Mandelstam variable, and T is also the Mandelstam variable. But there's a new parameter mu, which is introduced by hand as some sort of an IR regulator, because these amplitudes have an IR divergence. So these have to be introduced, and it sort of works as an effective graviton mass. More recently, if you've been following any of the stories with celestial amplitudes and so on, and the BMS, soft graviton theorems and so on, people would argue that every time you find such IR divergences, you've not really taken all the conserved charges into account. And this is probably related to a lot of the recent story. I don't really understand the details of how to fix this problem in this particular example, but it's very well studied these days. So a few comments first, which is that we just found some amplitude. There's no particle creation of Bremsstrahlung in this amplitude. It's sort of reminiscent of the Veneziano amplitude for those of you familiar with it. It appears that because we've had collision energies that are extremely high, that we've somehow extracted some Planckian physics from effective field theory. So you might wonder, okay, is quantum gravity so easy? What are we missing? Of course, what we're missing is essentially the punchline of this talk, which is that we're missing black holes. But what I want to point out is that black holes are missing in this picture in the following sense. We've assumed that impact parameters are very large, so larger than any other scale. But of course, when you have collision energies that are square root of S, there's a new scale that pops up, which is G Newton times square root of S. And when impact parameters reach that scale, so if they're no longer as big, people have shown, Veneziano in a beautiful paper in 2004, and Amati, Ciafaloni, and Veneziano in 2008, they've argued that these Eikonal amplitudes, when you take these impact parameters to be of the order of this emergent scale, that these amplitudes diverge, and that they argued that this suggests an intermediate state that is produced. So it's not clear how to push further with the flat space perturbations.
Sorry, could you explain what you mean by Eikonal amplitudes diverge?
They find that, so these amplitudes, I've explicitly assumed that impact parameters are much greater than any other scale in this theory. However, if you want to study the analytic structure of these amplitudes, you have to make sure you take into account effects that are subleading in the limit that you took. So when B is not much greater than G Newton times square root of S. And when you take these effects into account, this amplitude manifestly diverges. You can't see this in this formula because I've ignored all the subleading terms, but it turns out that there are divergent contributions that come in when you take subleading effects into account in the impact parameter. I just haven't written the formula.
Okay, thanks. But is this very specific to gravity? Because you're saying that there is some such G Newton-like scale will not be there in electromagnetism, for example.
Yeah, so I would hold back on making a very strong claim because possibly there are many things that I don't understand about the other things. So I don't know. I know that in gravity this happens, but is there such a thing, or can I claim that this is only true of gravity? I'm not 100% sure.
Yeah, I don't think such a thing would happen in also Yang-Mills, right? Because
Possibly not.
Eikonal approximation, probably not, because you won't be able to, because there is no other, you're not doing vertex corrections or anything, no, here.
Indeed, indeed. That's why it looks like gravity special, in the sense that quantum effects arise not only due to momentum transfer, as you would expect in field theory, but also due to some emergent scales. In this case, for example, the Schwarzschild radius. And that's what I want to go to next.
Yeah,
which
this
is
will be surprising to me that this indeed happens.
Yeah, and there's a huge body of work that Veneziano and all his collaborators have been doing on how to fix this, and they've tried a lot to model collapse and evaporation in this as you move away, as you take impact parameters to be smaller and smaller, to be of the order of the emergent scale. And there's a lot of work that goes into studying this analytic structure of these amplitudes.
So is Dwali's work on this quantum portrait of a black hole related to this also, this kind of Eikonal approximation diverging at these scales? And
so
that parameter becomes of this order?
I'm not 100% sure because I haven't followed the technical details of Dwali's papers. He has indeed looked at, for example, graviton scattering amplitudes, where you have, for example, a 3-point vertex for the cubic graviton interaction. So that gives you 2 to 2 graviton amplitudes. And then there are arguments about what happens when you have an intermediate state that has some degrees of freedom associated to it. But I haven't followed the graviton scattering amplitudes yet. It's something that I will get to. It's something that I hope to do in the near future.
Okay, thanks.
Good. So what I want to move now to is the work that I've been doing over the last couple of years, and this is to understand these interactions near the horizon when there is such an emergent scale. So in an ideal world, what you would like to do is take a classical solution, for example, that captures the formation of a black hole. So if imagine somebody very powerful gives you a solution, a classical solution of a collapsing star that forms a black hole, a time-dependent solution. You would like to take this solution, compute the graviton propagator, and then work out if there exists such a limit where you can compute all the Eikonal amplitudes similar to flat space. And then you would ask whether scattering amplitudes are unitary. But we're not in an ideal world. We don't have such a classical solution. Even if we were to have such a solution, finding the propagator on this background is extremely complicated. So, however, I return to the pictures that I was drawing earlier. So now imagine you're an infalling particle near V equals V0. You fall in, you collapse, and you produce some kind of an apparent horizon, but this is very dynamical. It's rapidly growing. But now think of an infalling particle near V equals V1. As it falls in, it's as though it falls into a black hole that already exists because the apparent horizon is so close to the event horizon. And you can, this is essentially what Hawking did. As you go to later and later timescales, that you can approximate this horizon, the apparent horizon, to be the event horizon. So you can, in principle, study the problem as though you're an infalling particle that's very close to V equals V1. And then there's outgoing Hawking modes. And the punchline of what I'm going to say today is that there are similar 3-point interactions or any gravitational interactions with virtual graviton exchanges that transfer this information from the ingoing particle to the outgoing one. Well, by that, I just mean that you can write down similar 2 to 2 scattering amplitudes. You can explicitly derive the scattering amplitude and show that this is just a pure phase, that it's unitary. That's the schematic picture of what I want to get to. So here's another picture with all 3 regions, the separated scales written down. So imagine you throw in an ingoing wave. As it hits the Regge-Wheeler, the classical potential, some part of it gets reflected, some part of it goes in. And what Hawking showed was that as it goes in, from the Schwarzschild horizon, only thermal radiation comes out. And what comes out has nothing to do with what goes in, essentially. That's the thermal spectrum. So what I want to argue here is that this picture gets modified as follows, that you have an ingoing wave that goes in, and it exchanges gravitons with the outgoing wave. And part of that information comes out as a first echo, but there's backscattering and then comes out again. But in the end, you will have one outgoing wave at future infinity that now will have modified Bogoliubov coefficients. And if you relate those to the ingoing mode that you started with, that this Bogoliubov coefficients are such that there is no particle creation, that there's no thermal spectrum, and the theory is unitary. What I will do in this talk is to focus on the scattering in the near horizon region. But then this is a paper with Panos and Olga that we wrote towards the end of the year that takes this 2 to 2 amplitudes and then glues them together with effects near the potential barrier, such that you can write down the explicit modified explicit Bogoliubov coefficients. But that I will not have time to do. But in this talk, I will focus on the 2 to 2 scattering amplitude nearby. So I want to argue that the mapping between the Bogoliubov coefficients in the near horizon region is mediated by graviton exchanges or interactions near the horizon. Are there any questions about this picture?
Can I ask some naive questions already?
Sure.
So after each echo, each echo gets weaker successively?
Yes.
So what I'm wondering is that the Hawking's computation actually holds for very late time, right? And
yes.
That is what his claim was, the very late radiation will be thermal.
Yes.
But if the echoes get successively weaker, how does it change this picture? I didn't quite get it.
What Hawking has done, and also what we did with the modified picture, is that what you compute is the mode at future infinity, which you can then expand in a geometric series to realize the echoes. So it's not a series that you manifestly realize first. You end up with a complete answer, which you can in a geometric series expand to find the echoes. And these are also sort of the gray body factors that you can include in Hawking's computation.
Yes, but I think the particular thermal nature comes from this analytic continuation from omega to omega prime. And
Correct.
there, this e to the power minus, there's only a particular coefficient that matters, right?
Correct. Correct.
And so as long as that coefficient is not modified, you will get thermal plus some small corrections maybe. But
precisely my point, exactly. That as long as you're in the near horizon region, as long as there's no modification here, as long as there's no correlation between what goes in and what comes out, and that there's a thermal correlation with the Rindler modes in the near horizon region, that the fact that there's an additional barrier will not change the result dramatically. Whereas if the whole spectrum near the horizon changes dramatically, and as I'm saying, that the outgoing modes near the horizon are no longer thermal, but they're related, you can explicitly write down a scattering matrix that's unitary, that you can also glue them to the barrier. The barrier doesn't restore unitarity. It's the near horizon dynamics of the gravitational interactions that restore unitarity. But you can also go to you can also write down the Bogoliubov coefficients by including effects coming from the barrier.
So you're saying somehow this resummation of the several echoes will create some strong effect that modifies the thermal answer completely? And
no. I'm saying that the resummation of all the gravitational interactions near the horizon. So think of arbitrarily many graviton exchanges in the near horizon region. That resummation modifies the thermal spectrum. The echoes don't do anything with unitarity.
That's okay, I understand this. Okay, no, I understand now. So echoes are not important. It's simply within each echo, there is a resummation that you're doing. That is what is responsible for modifying this monodromy, whatever of this.
Exactly.
Okay, I see. Thanks. Yeah.
So how do we think of this near horizon region? So you can think of, I'm going to head towards a definition of the black hole Eikonal phase. So what we start with is, instead of flat space, you start with spherical symmetric backgrounds. And I've written it in light cone coordinates u and v. And for a specific function a, this is essentially the Schwarzschild background. It turns out that if you use the covariant or de Donner gauge, it couples all the different spherical harmonics. So you cannot decouple all the partial waves if you use, and it's a gauge dependent thing. So, but there exists another gauge, which was in a beautiful paper by Regge and Wheeler in 1957, where you decompose the graviton into odd and even parity modes, as you see schematically written here. In this gauge, the off-diagonal components in the even parity mode are 0, and the odd parity mode have diagonal components of 0. That's essentially the gauge fixing piece. So if you look at the degrees of freedom, HAB is a 2x2 symmetric matrix. So this is you can think of it as a graviton on the light cone. So that has 3 components. K is a scalar field on the transverse sphere, that's 4. And X has 2 degrees of freedom. So the odd parity graviton has 2. And in total, they sum up to the 6 physical degrees of freedom. Good. So in this gauge, it's a tedious long calculation, but you can check that the quadratic action for the graviton, all the partial waves decouple. And because you have tensors now, these are not the same scalar spherical harmonics. We have to worry about tensorial harmonics, but all of this can be done. You can see the details in our paper. It also turns out that if you have transverse momenta that are very low, by that I mean that, think of the picture that I drew on the Penrose diagram, that the collisions only cause shifts in longitudinal directions, but not in the transverse plane. The transverse momenta are very low. It turns out that the odd parity graviton does not contribute to the theory, to my interactions. This is not something that is obvious, but it's something that you can check with calculations. Good. So what you can do now is to write down the effective action now on this background. So you have, as I said, the odd parity graviton does not contribute. So if you look at the quadratic action for the even parity graviton, you have the HAB field and you have the K field. The price you pay for choosing this gauge is that this is not diagonal anymore, that H couples to K. So the quadratic action, this is not in the diagonal degrees of freedom anymore. And then there's an interaction term, which is H mu nu, T mu nu, and then the scalar quadratic action.
Sorry, I have a quick question.
Yes, please.
So far, there is no approximation regarding the Eikonal and so on, right? This is completely general.
Yes, I will write down explicitly what the approximation is and where I'm making them and what consequences it has.
Thank you.
So far this is completely general indeed. And I have I've integrated out the sphere, but of course I keep all the partial waves. So these are all like the KK modes if you wish. Now in this theory, as you see, because the graviton degrees of freedom are randomly coupled, well, are coupled in a strange way, the propagators are defined by this equation, and the true propagators for all the modes are a curly P with 4 indices, a curly P with 2 indices, and a scalar propagator for the K field. And this is a very complicated thing. And in the Schwarzschild background, to my knowledge, we don't know how to solve this for the propagators. So now here's where to find these propagators is where I have to start making approximations because it's not generally known. So let's first look at Feynman diagrams on the horizon. So you see that I have 3-point interactions, as I said, and I want to glue 2 3-point interactions to make a tree-level Feynman diagram. And the graviton propagator in the middle can be mediated by any of these P's. So let's look at a couple of them. The first one is, let's say it's only mediated by the K field. And the one on the picture on the right is the one which couples HAB to K. It turns out that if you explicitly calculate this, and this is again general, you can show that regardless of what PAB is, just using symmetry properties, that this thing on the right vanishes identically. So what you're left with is the one on the left and the propagator that comes from HAB coupled to HAB. So now I make the first approximation of interest, which is at tree level, you can explicitly compute these.
Nava, I have a very short clarification question. So when you do this computations, is there some kind of restriction on the range of integrations of the vertices because your effective field theory only holds up to 3 GM or something?
Good. So excellent. So in this calculation so far, I have not explicitly found PAB. I have not found the propagators. I'm just arguing that at the level of using symmetries, you can show that the propagator from HAB coupling to K, that vanishes identically. But when I need to find the propagators explicitly, what I will do is to go near the horizon. So the propagators are only valid near the horizon.
So you are quantizing over this near horizon geometry, which is
exactly.
Yeah. So my question is that now when you do these integrations over the vertices, for example,
yes.
So are the vertices then restricted to lie in the near horizon geometry? That is
absolutely.
So R less than 3. So there is some kind of infrared cutoff.
Absolutely.
Or something.
Correct. So what you will see, a very nice picture emerges, which is a short answer to your question is that unlike in flat space, the size of the horizon provides for a natural infrared cutoff. So I don't have to put this in by hand, but it comes out of it. The second thing is that I'm only able to compute these things when I know the graviton propagators explicitly. And these I can only solve for in the near horizon region. But that's also exactly what I want, because if I have interactions in the near horizon region, then think of the horizon as some sphere with some fixed radius. Now I have particles that are interacting on the horizon or very near to the horizon, which means that the impact parameters between these particles is roughly of the order of the Schwarzschild radius. It cannot be much larger. So I cannot be in the approximation that I made in flat space.
I see. That's nice. But actually I was saying that whether you have some UV cutoff, sorry, I asked my question wrong. So because the interaction vertices cannot go beyond a certain distance from the horizon, right?
Excellent.
Was the field theory going to end there?
Good. I will come back to the UV cutoff in 2 or 3 slides.
Okay.
And you will see it explicitly.
So sorry, one brief question in this. Don't you have in the middle, when you have these graviton propagators, don't you have the possibility of K changing to this other mode HAB, because your propagator was not diagonal, right?
Correct. That's this diagram on the right, which I said, just using symmetry properties, I can show that
no, that's just PAB.
vanishes.
I thought you should have one where there should be an 2-point interaction between K and HAB, right? In the middle.
Yes. So what I mean is that if you, so I have a HAB couples to K via the curly PAB, HAB couples to HCD via the P with 4 indices, and K couples to K with the curly P with no indices. So the one that couples HAB to K has a propagator with 2 indices. And that's this one here.
Oh, so there is nothing with the 4 index object?
No, there's nothing with the 4 index object that couples to K, but there's of course a 4 index object that couples to itself. And that's this diagram on the right now, where I have a P with 4 indices now.
Okay.
So these are the 2 left. That's what I wanted to argue, that well, not argue, I wanted to just say that the one that couples HAB to K vanishes identically, and I'm left with these 2. And neither of these is vanishing.
Thanks.
And as Ayan just said, I'm focusing on the near horizon region. And in the near horizon region, I can explicitly calculate expressions for the propagators. It's a long, tedious calculation, but it can be done. I will show an expression for the relevant propagator in a couple of slides, where you will also see the UV divergences that Ayan was referring to. But for now, believe me that you can work out these propagators in the near horizon region. So approximately go to the horizon. It's not valid everywhere, but in that region, you can compute both these amplitudes. And here's my first approximation, where I choose my collision energies to be much greater than gamma times m Planck, where gamma is m Planck over m black hole. So think of a large black hole compared to the Planck size. So something that has the Earth mass, for example, but that can be very small in our units. So something that has a radius of 1 centimeter. Gamma is extremely small. For an Earth mass black hole, this is 10 to the minus 32 or something. So collision energies are extremely low because I've introduced this parameter gamma. In this approximation, you can see that the amplitudes on the left, you can explicitly calculate them. The amplitude on the left just contributes with a factor of S, whereas the one on the right has a very large factor compared to the one on the left, with this 1 over gamma squared in the denominator. So you can, as I said, you can write down the propagators explicitly, and you can find exact answers for the tree level amplitudes. And you will just, in this approximation, there will just be additional small correction. But what I want to say is that if I choose this limit, I can ignore the diagram on the left and only focus the one on the right, because there's such a huge separation of scales because of the emergent parameter gamma. Now, you can ask, when am I allowed to do this? I'm allowed to do this for as long as the black hole is much bigger than Planck mass. So essentially for the entire lifetime of the black hole, except the initial stages where the black hole is Planckian, and the final stages before it's evaporating, this approximation is valid throughout. So it has a very wide range of validity, where I'm allowed to throw away the field on the left, the propagator on the left. So for the rest of this talk, I'm going to focus only the one on the right, where the only important contributions come from HAB. Now, at quadratic order, I've told you that spherical symmetry can be shown and the partial waves decouple. But the moment you introduce interactions, you can have a coupling between, you can have Clebsch-Gordan coefficients that arise because you have 3-point interactions. But think of a collision event on the horizon. If you have 2 small particles with very small collision energies that are exchanging gravitons near the horizon, you don't expect these to ruin the entire spherical symmetry of the black hole. This is a small collision event that happens somewhere near the horizon. And the lifetime of this collision event is very small compared to the lifetime of the black hole. So there's an approximate spherical symmetry that's preserved. This is an assumption, or the approximation that I'm going to make, which is that I'm going to throw away Clebsch-Gordan coefficients. And I will say that all my angular momentum, Lm, so each external leg has an Lm associated to it, that the Lms just pass on. I represent these with solid lines, and I will just put 2 of the fields in the spherically symmetric configuration. So I just put L equals 0. In principle, I'm allowed to choose my external legs, meaning I can choose what I throw in, but I have to get out what I get out. So P3 and P4 in principle could have arbitrary LMs that are shared with some Clebsch-Gordon coefficients. So essentially what I'm saying is that because approximate spherical symmetry is preserved, that all the LMs get transferred to P4 and not to P3.
But isn't there a consistent truncation anyway to this spherical symmetry? This S
there is to quadratic order. At the moment you introduce interactions.
Okay, sorry, of course.
It's not clear, but it's approximately true, and this approximation is extremely good, as you say, because in comparison to a large black hole, a small event with two particles introducing something somewhere for a short lifetime, you don't imagine that ruins the spherical symmetry of the theory. I'm just trying to be clear with all the approximations that I make. Some of them are, I think all of them are reasonable. So this is one. The next one I'm going to say is I'm going to choose my external legs. As I said, we wanted one mode to be going into the black hole. So one mode to be traveling along the light cone, say U, and one mode that's going to be coming out of the black hole, which is the other one with a component only along V. If you compute this amplitude explicitly with these external momenta, it turns out that the momentum exchanged in this tree level diagram is 0. It's not something that you put in, but you can just compute the Feynman diagram explicitly. And it turns out that the dominant effect with the approximations that I made before is coming from the graviton exchange, which has 0 momentum. So the way you want to think about this is that there are particles that are traveling next to each other, that are colliding. In flat space, they were very far apart, highly energetic. They exchange a graviton with essentially 0 momentum. Now you have particles that are going closer to each other, not as far as in the flat space, but then because of this emergent scale of the size of the horizon, the collision energies are no longer very high, they're extremely suppressed, and the momenta of the particle do not change, but there is interactions that are mediated by 0 momentum gravitons. So the virtual gravitons at tree level are soft. So here's sort of a naive summary of all the approximations that I made. First thing that I've said is that there's a separation between effects on the longitudinal Penrose diagram compared to the transverse effects. So I've said momentum dominates only on the longitudinal piece. That's a dominant contribution. This is another statement that partial waves do not mix. So modes that are transverse on the sphere do not interfere too much, so they can be ignored. This is also something that Verlinde has argued in the paper that Ion was referring to. We wanted to capture physics where impact parameters are roughly the size of the horizon or some emergent scale in the theory. And we've modeled that by saying that we're capturing particle interactions on the horizon. So impact parameters cannot be large because they're confined to interact on a sphere within 3 GM. So roughly the order of the Schwarzschild horizon or less. However, they cannot be arbitrarily close because if you think of a generic collision, it's very unlikely that two particles will collide within an order of Planck length between them. Another way to think of this is that we know that the entropy of the horizon is finite. Therefore, if you just look at how many degrees of freedom there are, per Planck cell, there's roughly 1. It's a very naive argument, but it's not. But what I want to say is that it's a very rare event that two particles will collide at sub-Planckian distances, impact parameters. So I've chosen impact parameters such that they are much larger than the Planck scale, but of the order of the Schwarzschild horizon or less. Already you should have complained a little bit earlier, which is that near the horizon, I have curved space. How am I able to define my Mandelstam variables? The answer is that the effective theory on the 2D after integrating the sphere out is conformally flat. So I can make a Weyl transformation, and therefore I'm allowed to I can end up defining flat space kinematic variables in 2D. And I'm computing everything in the approximation where collision energies are much greater than gamma and Planck, as I said. So this is sort of how I define this phase with all these approximations. Good. Now comes what Oyan was asking for earlier. Here are the Feynman rules in this theory. So I'm in this 2-dimensional theory. I have scalar propagators with the solid lines and dashed lines, where one of them carries some LMs. And I have a graviton propagator in the near horizon region that can be explicitly derived, and you see it in the right top corner. So you see that the first 2 terms in the graviton propagator are roughly like what you would expect in flat space. because I'm in 2D and I'm in a conformally flat theory. So I have some factor that sits in front, and that factor FL captures the Schwarzschild radius RS, and it has some dependence on which partial wave I'm looking at. And all the partial waves have decoupled. So I have an infinite tower of 2D theories, essentially. All of them interact within themselves. However, there's a momentum dependent piece, which is the last term in the propagator, where you see that all the Ks appear. So these are your expected UV divergences. If you integrate over all possible momenta and virtual momenta, you will get infinity because this thing blows up. And that's the non-renormalizability of the theory. I haven't solved any of those problems. It's just there. However, now put K equals to 0. This is finite, and the graviton has essentially gained an effective 2D mass near the horizon. So what I've traded for is a massive massless graviton in 4D, but I've integrated out the sphere. And because of the curvature, there's a potential, there's a mass term that appears in an effective sense in the 2D theory. So
this is like a Debye type mass because it's completely longitudinal, right?
Yes, indeed. So it's not a physical mass nothing has changed. It's just an artifact that allows you to calculate things. And this turns out because of the natural scale provided by the horizon. And once you write down this theory, you can see that the vertex is now specified by this emergent coupling constant that I've defined as gamma. Good. So now, if I want to compute amplitudes in this black hole Eikonal phase, there are 3 scales in the problem. I have the Planck scale, I have the black hole mass, or the size of the black hole, and I have the energy of collisions that I choose. All the amplitudes that I'm going to compute are going to be perturbative in square root S is much greater than gamma and Planck. So I will look at the leading contributions in this regime that will have the impact that only soft diagrams contribute, which means that only gravitons that do not exchange momenta, the virtual gravitons carrying no momenta, only those contribute. It's an outcome of the calculation. But I will resum infinitely many Feynman diagrams, all the ladder diagrams like one was able to do in flat space. That is essentially the statement that you capture all orders of perturbation theory. So even exponentially small contributions in gamma. So that's a sum over infinitely many Feynman diagrams. So here are the pictures again. Now remember that solid lines carry angular momentum, dashed lines do not. So here I will call this the conserved channel. So at one loop, if all my vertices have one dashed line and one solid line, that at one loop, my angular momentum stays on top of the diagram and only dashed lines emerge. The external legs are dashed at the bottom. So I call this a conserved channel because angular momentum stays on top. At 2 loop, however, you see that the only possibility is that the solid line gets transferred to the bottom if I join more loops. So you can just put these together and you just observe that all even loop diagrams are what I call transfer channel. All odd loop diagrams are what I call conserved channel, where the angular momentum just stays on top. In principle, you have to resum all of these things. I won't go through the calculation, but you can explicitly write down the general n-1 loop amplitude. So this is with n virtual gravitons exchanged. So if one graviton exchange, it's a 0 loop, it's a tree level diagram. And this is given in terms of the propagator that I said, which has 4 indices. And only one of the terms contributes because of the choice of external legs. So I wanted to model something that goes into the black hole and something that comes out. And all of this amplitude is given in terms of some function chi. And this is a generic feature of all Eikonal approximations, that your general amplitudes are given in terms of some one definitive function. And if you look at the Eikonal function chi, you get a delta function. So the soft limit is enforced upon us. In principle, this needn't have been the case. If you do this calculation, had you found out some dependence on k's, you would be in trouble, because that means that you would have had to integrate over all of momenta and you would run into non-renormalizability issue. So it turns out that in this phase, only the zero momentum gravitons are important, and it's sort of enforced upon us by the calculation. You can write down all these amplitudes, so all the transfer and conserved channels, and you can explicitly resum all of them, and you get a very simple, beautiful expression, which is at the bottom right. So what you see here is S, which is the energies of the center of mass collisions, and you have this function chi. If I substitute for what this chi is, I know the propagator, I know what gamma is. So if I substitute for this amplitude looks like this. So, and I wrote S in terms of momenta. So that's P in times P out. Remember that I'm using light cone coordinates. So it's P dot P if you want. And I've substituted in the first line, I've just substituted for what chi is. So in terms of the propagator that we've chosen or that emerged from the calculation. And in the next line, I've just substituted for what gamma is. Gamma, as I said, is m Planck over m black hole. So it turns out that after you resum all of these, you get a nice exponential where the dependence on the horizon goes away. And the only parameter that's left are the collision energies P in and P out and G Newton. This is the result of the calculation. Now this is, if you ignore interactions, let's say you ignored all the gravitational interactions, you would only pick up the -1 term. So if you just analytically continue my amplitudes with no gravitons exchanged, when n equals 0, you would just get this -1 term. So the most important part of the scattering matrix, is completely governed by 2 to 2 interactions, as I said, and that's given by this exponential. And this exponential is manifestly unitary, it's a phase. So the scattering amplitudes are unitary, and that's essentially the result that comes out after you compute all of these diagrams in the controlled approximation. Just like in flat space with the Eichelberg-Sechsel metric, there's another interesting story with the shock waves for the black hole. And this amplitude is very closely related to this. And there's all kinds of things that one can say about chaos and so on. Again, I think I'm running out of time. And I haven't.
Nava, I just wanted to ask a very trivial question. So yes, essentially the in vacuum and out vacuum are not the same, right? And that's the whole point of why you need to compute this. Because normally in scattering theory, we say that, okay, I mean, there is some in vacuum and out vacuum, but the whole problem comes is that the out vacuum is essentially a thermal state of the in states.
I would phrase that slightly differently.
So no, my question is here, so why you didn't have to compute all these things? I mean, I never looked that you had to compute any Bogoliubov coefficient ever.
Excellent. In this so let me go back to this slide. So I agree with you. The statement is that how do you know that the in vacuum and the out vacuum are different? You go through Hawking's calculation, and then you assume that there are no gravitational interactions. And then you find out the Bogoliubov coefficients and you see that they are thermal. So you know that the out state looks thermal with particle creation. Now, if you take, instead of Hawking's free field approximation, if you do exactly what Hawking told you to do, but now include all the interactions in the near horizon region with all these amplitudes, you produce some kind of an S matrix in the near horizon region. And then you ask the same question at future infinity for the asymptotic observer, and you now recompute your Bogoliubov coefficients.
I think what you're doing is something a bit different. I guess you're mapping the problem to flat space by using some Weyl transformation. But the whole point is that somehow I think you are suppressing this Weyl factor, which, I don't know, in a way,
there is nothing suppressed here.
There is something in the zero mode, in this Weyl factor that you're ignoring, or that's.
No, I'm not ignoring any Weyl mode. The fact that I make a conformal transformation has the effect that I have additional potential terms. These are not thrown away. It's just a mathematical trick where all the physics is captured. I'm not mapping the problem to flat space. I'm just observing that in the near horizon region, the theory is actually flat. That's the same statement that the theory is Rindler. The space-time is Rindler.
But even in Rindler space, you need to compute some Bogoliubov coefficients after all.
Bogoliubov coefficients are things that relate modes at future infinity with modes at past infinity. That's what Hawking computes.
Essentially, it comes from the fact that the in vacuum and out vacuum are not like, so usually if you just do flat space S matrix, the out vacuum and in vacuum is simply related by a phase, right?
How do you know
that? Vacuum, well, that is a theorem. That's a basic theorem.
Correct.
So basic quantum theory textbook will tell you that
Correct.
The out vacuum is some big phase multiplying the in vacuum. But this is not the case anymore in the black hole, right?
I disagree with that statement. I'm saying that the fact that this is not the case in the black hole is a conclusion that you get if you ignore gravitational interactions near the horizon. I'm doing exactly the same calculation as Hawking in the following sense. Hawking computes Bogoliubov coefficients between out vacuum and in vacuum, ignoring gravitational interaction. I do exactly the same with including interactions in the near horizon region. I'm just saying that the out vacuum is again related by a phase, just like what you would expect in quantum field theory.
Yes. So I would say what you're doing different is that you're treating different conformally related vacua to be the same. I mean, you still have many different vacua. you're treating all vacua that are related by conformal transformations to be the same. I mean, you're calling all of them to be the same vacuum.
Why do you say that?
Because as Ayan says, you have put all of the physics in the Weil transformation factor. You have ignored all of this. You say that all of the physics is there. What I'm saying is that it is there in the class of vacua that you're treating as one vacuum.
Let me put it differently. How do you define your vacuum? With what modes? You would define your vacuum at Scri plus or Scri minus.
Yes.
Right? Near Scri plus or Scri minus, what I'm doing here has no role in the sense that the conformal transformation that I'm doing is only to capture near horizon physics. I'm not changing any definition of my vacuum at Scri plus or Scri minus. Those remain exactly as you had before.
But it might be that the conformal transformation at Scri minus and at Scri plus are different transformations.
I'm not making any conformal transformation at Scri minus or Scri plus. That's what I'm saying. That's why I'm saying I'm not doing anything with the vacuum at future and past infinity. The conformal transformation that I'm making is only in the near horizon region, and it's a mathematical trick that does not ignore any physics. So I'm not changing the definition of vacuum at Scri minus and Scri plus.
To put it, I think he's just looking in this box part that he showed in his first figure.
Yeah.
Yes, matrix there. But I don't see how that itself being unitary can change anything of Hawking's result. But anyway, you can go down, you can go ahead, maybe you can.
Yeah, unfortunately, I haven't. So what I wanted to say here was that as you said earlier, Hawking's result doesn't change because of the potential barrier, just like here. Hawking's result is thermal because of the near horizon structure of the theory. That is thermal, the Rindler modes, and therefore, whether you take the barrier into account or not, at infinity, you produce these thermal modes.
Well, yes, no, I mean, okay, anyway, I think you're right, but because you can just look into very late where it only grazes the horizon, you're right, but at the same time, it depends on that, but you still have to look into this bifurcate horizon and connect to Scri minus and Scri plus somehow. So I think this is something, anyway, we can probably debate this later. We can perhaps finish your talk first. There's more question.
Did you hear me? Sorry. Yes, just a small comment. So what Nava is trying to say, maybe in some different words, is that in the second picture, if you forget about these wiggly lines, then you get the thermal spectrum and everything that Hawking was saying. So the only difference comes because of these wiggly lines, of this exchange of gravitons.
Yeah, but then suppose if you turn on if you take G Newton to 0, you should recover Hawking's result or not? I mean,
yes. That you get exactly.
Yes,
Let's look at this amplitude. Look at the second line of this amplitude that I've written down. If you put G Newton to 0, you will just get no scattering amplitude, and you will just get Hawking's result.
Where is Hawking's result again?
No, I just mean that the scattering amplitude it does not exist. So if I take this amplitude with G Newton equals 0, and then I map this now to go to future infinity, I will get Bogoliubov coefficients that are thermal. I just haven't written the explicit Bogoliubov mapping because I thought I wouldn't have time to discuss everything with the gluing, but it's in the paper in 2012 in last month with Panos and Olga, where we explicitly write down the Bogoliubov coefficients. You take that coefficient, you put G Newton to 0, you will just produce Hawking's result, just the thermal spectrum.
I see. Okay, so yeah, fine.
So this is exactly where I wanted to end. And just to conclude, with probably more questions and complaints, what should you take away from what I just said? I want to keep this very short so that there are 3 punchlines that you remember. First, I've defined for you a new phase of quantum gravity, which I called the black hole Eikonal. And in this phase, the information paradox is resolved in the ways that I've described. And you might be worried that UV completions might have been necessary for this, but also from more recent studies that have been in an orthogonal sense discussed, we also see that semi-classical gravity with some non-perturbative corrections in a very controlled approximation is sufficient. And I've shown you dynamically how this happens with virtual soft gravitons, where no UV completion was necessary precisely because I didn't have to take into account a momentum exchange. There are no firewalls because the center of mass collision energies of the collisions are extremely low. So even though in flat space, you might have thought that energy collisions are extremely high, and as you bring the impact parameter to be very small, that this would give you some notion of a firewall where you experience very large collisions. because of the emergent scale, the collision energies are radically changed, and there are no firewalls in that sense. Because I haven't discussed the gluing with the Regge-Wheeler potential, there's a lot more to be said about chaos or quasi-normal modes and how they get modified, but that I haven't had this time to discuss. And what are the things that you can do for the future? Here's a toolbox where you can possibly look for hints for ultraviolet physics by including perturbatively corrections away from the black hole Eikonal phase. In particular, you can ask, the one diagram that I threw away was the one that was mediated by the field K. You can ask what happens if I include that field and look at, say, one loop corrections. I might not be able to resum everything like I've done here, but possibly you get some corrections that give you some hints on how to think about ultraviolet physics. All calculations, and there's a lot of work that has gone into the flat space Eikonal regime, all calculations can essentially be repeated in this setup in the black hole Eikonal regime, precisely because amplitudes have been computed almost identically. It's just that the approximations have changed a little bit, taking into account the emergent scale. You can ask, for example, I've had this theory which is unitary throughout because all the dynamics is unitary, but how can I think of the Bekenstein-Hawking entropy from this picture? It's not a very natural question that you would ask in a unitary theory, how some semi-classical effective temperature comes out, but there's probably some answer because we see that gravity is apparently very good at this. You can also ask, instead of matter fields that are just scalar fields, what happens if you include standard model fields or higher order interactions? Or you can also try to repeat this calculation in ADS and it will follow through almost entirely, because in ADS, you will just have an extra contact term coming from the cosmological constant that will change your potential, the propagator slightly, but then the calculation is essentially doable and you can ask for a CFT interpretation and so on. There are many other questions that I haven't listed here that are very natural to ask using the tools that I've presented here. With that, I thank you for your attention. I'm happy to take more questions, complaints, criticism.
Okay, thanks for this talk. So any questions?
Hi, thanks for a very nice, clear talk. I just wanted to ask, so these modifications you make is only at the horizon, presumably, right? This
yes.
property. So that is independent of the asymptotics. So so it shouldn't matter whether it's flat, asymptotically flat or ADS and so on, right?
Exactly.
Okay, so you're hopeful that you can do this for...
I'm certain that I can do this. It's just that I haven't done it yet. But I'm certain that the calculation at a technical level will follow through precisely for the reasons that you've said.
Okay, could you just go back a few slides? I mean, at some point you had a P at 0, this propagator XXYY
yes.
at 0. So is that what is equal to what you wrote in the next slide, which is this GN in the
Yes, so if you look at the last expression at the last equality at the bottom, that's my amplitude.
Right.
That has a chi in it. And the chi is defined, or the chi turns out after the calculation to be defined by P at 0.
And that is the same as what you wrote in the next slide, which is, was that?
Yes, I just substituted for P in chi and I substituted for chi in the last equality. And this is exactly what I wrote.
Thank you. Yes.
And perhaps a comment, now that this question has come up, perhaps a comment that would help address the questions before. Imagine somebody gave me the graviton propagator, not just in the near horizon region, but everywhere for the entire Schwarzschild spacetime. Then I wouldn't have to make this conformal transformation, whatever. I would just know the graviton propagator everywhere. And then if you trust this logic that it's going to only be projected into the soft sector, I will have some momentum independent constant that will contribute in my answer that will change this answer slightly. So that will change some numerical factors in the final answer, but the fact that the exponential and the pure phase comes out because of interactions will probably remain the same. It's a bit of a leap, but it's not hard to believe precisely because this is projected onto the k = 0 sector.
Nava, just one thing. So if you look into the Verlinde papers, they also talked about such an S matrix, but you're saying it was not computed by your advanced methods, like on the near horizon geometry, but rather say that space or something. I don't know. I mean, maybe there is some, but I think what they conclude was that this S matrix, if you put it in, it still doesn't change Hawking's results fundamentally. It simply gives some corrections to the Hawking's result, perhaps, but not. I think
I don't remember if that's the claim that they make, but if they make that claim, I think this computation disagrees with that claim, because what I want to show, what Verlinde and Code argued was that First, they observed that there's a separation of scales on the transverse spacetime versus the longitudinal. So they said we can ignore the transverse sphere and we can just focus on the longitudinal one in the 2D theory. And then they used the shockwave computation of Drey et Hooft to reinterpret that as a scattering matrix. And it's something that I unfortunately didn't have time to discuss, but if you look at what et Hooft has claimed in the partial wave basis for the scattering matrix should be, it looks extremely close to this. There's a discrepancy of a small factor. Here in the denominator, I have L squared plus L plus 2. Et Hooft has L squared plus L plus 1. It turns out that if you take, I've integrated over all metric perturbations in the approximation. So I looked at G mu nu plus H mu nu, and H mu nu is the one that propagates virtually between the vertices. And I've essentially integrated all of them, all the metric perturbation. If I project onto only on-shell degrees of freedom, such that H mu nu are those that satisfy Einstein's equations of motion, then I will reproduce Ferlindes or et Hooft's results. So,
okay, so suppose, how do I compute something like this vacuum to vacuum amplitude in this process? I mean, if I do that, I should get a phase, as you're saying, only a pure phase, but I don't understand in what limit I should recover this.
Excellent. This is what you would do.
The vertices. So you are saying your claim that I would be recovering this. I mean, I don't really get it. Because Hawking's original computation is simply vacuum to vacuum amplitude, right? That's all.
Yes. As I said, this amplitude is in the near horizon dynamics, but I can go further away and write down Bogoliubov coefficients that give me vacuum to vacuum amplitudes in the sense of this picture here. So I focused on the region between the pink and the blue lines, but then I can extend this beyond the potential barrier. There's this clear separation of scales where I'm just propagating fields in flat space. So there's a consistent way in which you can glue these two together with boundary conditions at the potential barrier. And that can be consistently done also because plane waves near the horizon and plane waves at infinity.
That's what I'm saying. You don't need to go beyond the potential barrier, actually. You can think like going to extremely early time and extremely late time. Then the horizons do intersect scry plus and scry minus. If you go, so you don't need to actually go beyond this potential barrier.
When you say the horizon intersects scry plus and scry minus, there's a problem with this picture, right? That point.
Because if you go to very, very late time, they do, no?
They do, but then that's a picture that's very misleading because it's a highly singular point. If you're on scry plus, you would think that that sphere is infinitely big. If you're on the horizon, you would think that that sphere is 2m, and you identify these 2 points at that point. So it's a very singular thing that happens because of the conformal diagram. I don't know how you want to think of that point.
I don't know. I mean, I feel something is kind of missing in this computer. I just get a feeling. Maybe I should read your paper more carefully.
The thing that's missing is all corrections that come from subleading contributions when the black hole is not as big compared to the Planck size. Everything else seems to be captured.
Okay. So thanks for this very nice talk. It was very interesting.
You made a comment about firewalls. Would you make a comment about fuzzballs?
Excellent question. So I can think of one way to make a disambiguation between so think of these echoes again. I'm fortunately at the right picture. Regardless of what scattering matrix you have near the horizon, whether this is a scattering matrix that I wrote down, or if you just by hand put reflecting boundary conditions, no matter what you do, you would have this picture of echoes. However, depending on what scattering matrix you have in the near horizon region, the exact echoes will differ. In what I've computed, I have not introduced any new arbitrary parameters in the theory. Whereas in most fuzzball models that I know, they can also compute outcoming echoes and how they behave, and they will have some additional parameters.
Yes.
And in that theory, you will be able to tell them apart. If what I'm doing is correct, if let's say you were some observer who's able to measure these echoes, you will be able to tell them apart because I don't have any way to tune them to fit data. I just have all the parameters that I have not introduced any new parameters, whereas they've had to introduce some parameters. So that's one way to tell them apart. Physically speaking, I've not introduced any new structure near the horizon. Physics looks essentially like what Hawking would have said. infalling particles do not feel outgoing particles because their momentum does not change, because they only exchange zero momentum gravitons. So they don't even feel like they're moving or changing direction. Nothing happens to them, but there's still interactions that are important. So in that sense, a low energy observer would never detect anything. So there's no structure that is apparent from this calculation.
Okay.
But there are very refined formulations of the fuzzballs. I don't know if, I'm not sure if they would, there's the strong version, there's the weaker version. I'm not sure which version that I can compare to.
Yeah.
But the statement that I can make is that low energy observers would never see any structure.
Okay.
Thanks. So, any further question? We can have one last one, perhaps.
Nava, can I ask something? I don't know if you remember or anybody else. So in the fastball story, are there claims that if you make, I don't know, a superposition of a lot of fastball geometries, you can make a black hole geometry or something like that?
I think the claim is that if you pick any, so I know the story in the supersymmetric cases because that's where the picture is very clear. If you pick any supersymmetric microstate geometry, the claim is that near the horizon, they look very similar. And because they're also extremal, the singularity is very far away. But what happens is that in the microstate geometries, the singularity is not a singularity, but it has a smooth cap. But that difference is only very far in the interior of the black hole. But near the horizon, the physics is the same as a black hole. And a low energy observer, I think, wouldn't be able to tell the difference. That's how I understand it. But then the final claim would be that because the black hole has this singularity, you would like to throw that away as something that's disallowed, but interpret the entropy and the emergence of a horizon as a superposition of all of these microstates. And because all of them have a near horizon behavior that is very similar to black holes, that's where we get our IR puzzles, if you like, or semi-classical puzzles, but then they're resolved because of the smooth caps in the interior, and these are not really horizons.
Right, so these extra parameters that they have, they might get averaged to zero or something like that.
Possibly, I don't know.
Yeah, I don't know.
But
I don't know
the story is far less clear if you're far from extremality, which is what we are with the Schwarzschild solution, and if you don't have supersymmetry. I don't know how much is known, how much you can extrapolate from the supersymmetric stringy examples to arbitrarily far away from extremality. I don't know what is known, what is not.
Not much.
Yeah, that's what I would have thought, but I wouldn't like to be the one making the claim.
Okay, thanks everybody for the nice discussion, and
thank you very much.
Nava again for the very nice talk. So we conclude now. So see you all next week. It will be a talk on by Upamanda Maitra on his recent paper with Sandeep Trivedi on second order formalism of JT gravity. So see you all next week.
Thank you.